So we saw how breaking down a finite region of space into tiny rectangular regions gives us a way of perhaps figuring out the total flux that flows out or total flow outside of this finite region by appealing to the analysis we have done in our previous video, where we related the flux density with the divergence of the flow and the circulation density with the curl. Now, in the process, we discovered that let's say we have two rectangular loops which are adjacent to each other in this manner, then the net contribution of the flow, which comes from a shared edge or a shared segment, like the one that I've drawn here, is zero. And that's physically, that's intuitive, because if I have a vector, if I have some flow which is flowing across this edge, then let's say this is fluid, then the fluid that flows out from region 1 just enters region 2. So this common edge does not really contribute to the net flow outside of these two rectangular regions if we look at these two rectangular regions together. Now we can extend this idea and let's say now we have four such, we look at four rectangular loops which are neighbors or adjacent to each other. So therefore they share these edges, 1, 2, 3, 4. So what we'll find is that the net contribution of the flux, which comes from these common edges, is just zero, right? And building on this logic, by the way, as a quick exercise towards the end of the last video, I encourage you to try out what happens to the tangential component of the vector fields. And perhaps you would have discovered that just like the normal component, the tangential components of the vector fields across common edges again cancels out. So in a nutshell, what this tells us is that let's say I have these four rectangles now. Maybe we label them 1, 2, 3, and 4. The total flux or the total flow away or outside of this, the total fluid or total vector which is flowing outside of this region, the contributions will only come from edges which lie at the boundaries. So this edge will contribute to the flux, this edge will contribute to the flux, this edge, this edge, this edge, and this edge. Whereas all the internal edges, which are common, the net contribution will just be zero. Now, if I extend this logic even further and add more and more of these rectangular loops, perhaps you can fill up any arbitrarily shaped finite region in space. And this is kind of like the reverse engineering of what we did last time, where we had a finite region of space and we broke it down into these tiny infinitesimal rectangular loops. Today, I'm just doing the inverse of that, where I'm just putting these blocks together to construct the finite region of space that we're looking at. Now, what will happen is something interesting. As we keep playing this game and I keep adding these sort of rectangular loops in this manner, and you in our mind, maybe we should have this intuition that eventually we'll be looking at these rectangular regions in the limit that their area or their size tends to zero. So that's why we're referring to them as infinitesimal rectangular loops. So as I populate more and more of these rectangular loops, like this, and perhaps like this, eventually you'll see that all these internal contributions will just cancel out. So if I sum up the flux, the total flux across each of these infinitesimal rectangular loops, the only contribution, the net contribution of that would come only from these residual edges which lie at the boundary of this region. For instance, this one, this one, this one. And as you imagine shrinking the size of these rectangular loops even further, you will see that the boundary points, these the edges which lie at the boundary, start mimicking the shape of the actual boundary better and better. So one way of expressing this mathematically is that the total flux, so let's maybe look at the example of four rectangular loops in this manner, just to make this idea a little clearer. And we have 1, 2, 3, and 4. So we can express this in the following form. We can say that the net flux, del F perhaps, is del F1 plus del F2 plus del F3 plus del F4. And I can write this as summation del Fi, right? That's the flux across all of these rectangular loops. Now, if I apply it to this particular finite region that we're looking at, I can still use the same, and let's just say that I goes from 1 to perhaps we have n rectangular loops if we have finite number of these. Now, in the previous video where we established the relation between the flux density, or rather the flux and divergence multiplied by the area, I can write each of these del Fi's as the divergence of the vector field. That's sort of where the vector field is defined. This V is defined at the midpoint of that rectangular region. So that's the divergence of the vector field times the area of this rectangular region. Maybe I'll use the symbol I just to denote that this is focusing on the ith rectangular loop. So the total flux, if I were to sum this up, would look something like this. So in other words, this will look like sum of the divergence across each of these tiny rectangular loops times del x, del y. That's the area area of the ith rectangular loop. Now notice that there are two of these del x, del y. So technically, this is a double summation, right? Where you sum over the ith coordinate, you sum over the xth coordinate, and you sum over the yth coordinate. So the total flux across this finite region is double summation of the divergence across all of these tiny rectangular loops. And in the limit, when del xi tends to 0, del yi tends to 0, the double summation del dot vi del xi del yi can be written as double integral of the divergence of the vector field dA, right? Where one of the integrals is over the x coordinate and the other integral is over the y coordinate. And that's the total flux across this finite region, right? Now, this is one expression, one form of what is called Gauss's law, Gauss's theorem. Now, an interesting thing that we can add to this Gauss's theorem is that since we've looked at the analysis quite carefully, we figured out that the net flux, the only vector field that will make a contribution to the next net flux would be the ones that's coming from the edges of this rectangular region. So for instance, if I fill this up like this edge kind of mimics or follows along the actual edge of the region that you're considering. So the vector field, the V field, which exists right here, is the only one which will really contribute to the flux outside of this region, or the flow that's leaving, or the fluid that's leaving this particular region. So in other words, the flux here can be written purely in terms of the boundary of this finite region. Or in other words, I can write, since this is a closed loop, I can use the circular symbol, and I'll point you to a link where we've discussed this in detail, and we can put an arrow here to indicate that we are traversing this closed loop in the counterclockwise direction. So the net flux will come only from the vector field at the edges of this region. And in order to take the flux, we take the vector field and take its dot product with the normal at that particular location. So it's V dot the normal vector, right? The unit normal vector. And when you integrate this, when you sum up all of these contributions, that's the net flux. And this is equal to the divergence of the vector field defined in the following manner. And so in this form, we express this as the fundamental theorem of divergence. Now, notice one thing. There is a very, very spectacular similarity in the structure of the fundamental theorems which we have been deriving so far. For a one-dimensional function, when we integrate, let's say I integrate a function, small f of x dx, let's say from point A to point B, the result of this integral is, if capital F is the antiderivative of small f, the result of this integral is f capital FB minus capital FA, right? Which means that if I sum up the local values of the function in the region A to B and multiply it by dx, the net result is given by the value of the antiderivative purely at the boundary points of this region, right? So perhaps we have this curve which goes from x equals A to x equals b, and that's the x-axis, and that's f of x, then the value of the integral over this interval only depends upon these endpoints, right? It's capital F evaluated at b minus capital F evaluated at a. Now, if you look at this expression, we are taking the vector field in the interior of this region, right? That's the interior of this region. We are calculating the divergence across each of these rectangular loops. We are summing up that contribution, which is where we get this term from. We're summing up that divergence contribution for each of these. So that's locally defined. This vector field is locally defined in the interior of the region. We're summing up the divergence over all of these interior regions, which gives us this double integral. But in the end, this entire summation or this entire integral only depends upon the value of the vector field, which is defined at the boundaries of this region, right? And so this kind of a correspondence between what exists in the interior of the region to what is defined solely at the boundary of the region is the spectacular sort of symmetry in the structure of the way in which all of these fundamental theorems are written. And by the way, this is also true for the fundamental theorem of gradients, which we've derived before. And I encourage you to have a look at that video and check it out for yourself. Now, this exactly the same idea you can extend further and try to figure out the fundamental theorem of curls, which is instead of considering the normal component, this time consider the tangential component of the vector fields and see if you're able to derive for yourself Stokes' theorem and the fundamental theorem of curls. If not, do check out the next video, which will be there very shortly. Thanks for watching.